All right, hello. Hope you're doing well. Welcome to Chem 1C, and we'll start off chapter 15 here with a video on rate laws and specifically determining rate laws. And the type we're talking about in this video will be differential rate laws. These are the type that we usually mean when we say the rate law for a reaction. We'll start with a question that goes over rates of change. When we have a chemical reaction, we're measuring, rate. That's going to be defined as a change in concentration of something over time, or you can write it as d concentration over dt, like a differential form. So there's all kinds of formal ways you can express this. One main point I'll make right here in the beginning is that normally with chemistry, we just have things representing positive rates. So if you have a reactant, because it's being used up, like B is here, we have a rate of disappearance of B, but we're just going to say that that is this value, right? If you actually measured the rate of disappearance or the rate of change of B, it would be negative 0.48, right? If you're using that up. But as just a convention, we're going to just again use positive numbers for rates. Something to be aware of, basically. Okay, so we know the rate of change of B. We want to find the rate of change of C at this point. So we're looking for this here. And what we know is that this chemical reaction has these balanced coefficients. And based on stoichiometry, the rates of change of reactants or products won't always be the same because of stoichiometry. So what we can do is basically say that the rate of change of C is, if we look at these, going to be 2/3 the rate of change of B. Again, just assuming all positive values. So we have 2/3 of 0.48, which gives us 0.32, same units molarity per second. Okay, so I hope that makes sense. Again, just using a stoichiometric ratio from B to C. Okay, let's move on to determining a differential rate law using rate table data. Most of the problems covering this, this general topic involve analyzing these tables. So you definitely want to get some practice doing this. It'll be well worth it for the tests, I'm sure. Also, I'm sure in Alex they'll have a lot of topics related to this. And again, we're determining the rate law. So we'll start with rate equals K times A to some power times B to some power. Okay, so basically I'm getting this from, again, this reaction. If we look at, we have just two reactants, A and B. So those reactants are going to be in the rate law. Generally, you're just going to have reactants in your rate law. So that means here we're expressing a rate in terms of reactants. This is called a rate constant, which we'll get to in just a second. A little lowercase k. And these here, x and y, are called the orders. And those are determined by experiment. So that's essentially what we're trying to do in these problems, is find the orders. Okay, really what it comes down to, kind of the starred short formula, is that you have a change in rate, and that's equal to a change in the concentration of something raised to the order, right? That's, if I could summarize the basic method of doing this, is you're trying to figure out, using this little quick formula, what the order is. So for Let's start basically by saying to determine the order for A. So we're going to look at experiments where only A changes. So if B is kept the same, let's say B is the same in 1 and 3, and then we have A changing, right? So we're going to look at experiments 1 and 3 because only A changes. And then the quick way is just to look at the experiments and see what's happening to the rate. And if you divide the rate 3 by the rate 1, or rate of experiment 3 by rate 1, you get a factor of 2. If you divide the concentration of A in experiment 3 by in experiment 1, you get also a factor of 2. It's easy if the numbers are, nice and round like these, where you can just kind of look at them. Otherwise, plug it into your calculator, divide them, you should get some kind of number. And then that just goes in here. So the change in rate would be 2. The change in concentration is 2, and then you have the order, right? So again, this is change in rate, change in concentration. So this therefore gives x equals 1. And then we're going to look at determining the order for B. Look at experiments where only B changes. So going back up here, let's see, erase this to make it not too confusing. A is the same in 1 and 2, and B is changing. So what we're going to do is then, let me just write this down, 1 and 2, only B changes. Okay, so what's happening to B is it's doubling. What's happening to the rate is it's increasing by a factor of 4. Again, if you divide those, you can verify that. So we go down here, we have our formula. Change in rate would be 4, change in concentration would be 2. That whatever you use for the variable doesn't matter, x, y, whatever, pick your favorite letter. And then this is easily solved to be 2. 2 squared equals 4. Normally these are like small integers like 1 or 2. You can also get half numbers like 1.5 order or something like that. That's fine. But generally these are the most common types you'll get, like first and second order. Another way to refer to these, by the way, is like y equals 2 is just saying second order. So the rate law would then be rate equals k times a to the first power, and then b to the second power, or squared. So that's our rate law. And then the overall order of the reaction is pretty simple. We just add up the orders. So we have first order and second order. Let me get out my calculator here. That's a third order overall. All right. Nice and easy one. We'll get into kind of what the orders mean later on if you're curious. It kind of has to do with the way the reaction proceeds and what reactants are in, like rate determining steps and things like that. Okay, so rate constant, also pretty simple problem. We're just basically solving for k. So once you have your rate law, then we can just solve for k. So basically plug in the numbers from any experiment you want to choose because k is a constant. So we have a rate law. Let's say we look at experiment 1. So the rate is 1.2 times 10 to the negative 4. I'm going to include the units. That's going to be 4 molarity per second. And then we have K. And then if we look at A is going to be 0.12. and B is going to be 0.15. So we have 0.12 and 0.15 molarity squared. So I would include the units. I recommend that because the units of K will vary, and they will be important to have the right units. I know it's kind of a nitpicky thing, but it's just the way, you know, tests and homework operate, is they're picky with units. So what I got for the value was 0.044, and if we analyze this, it's 1 over molarity squared per second, or sometimes written like this because capital M is moles per liter, right? So that's the same as moles. If you have molarity in the denominator, same as liters over moles. So same thing here. Okay, so I hope that makes sense. And again, any experiment you choose, you should get the same value for K since it's a constant. All right, so now we have a reaction with 3 reactants, as we can see here. And this is, you know, 50% more fun. It's just mathematically proven. So we, it's a good one to practice. I would recommend, again, doing these just in general, maybe doing the worksheets on your own, trying them first, and then if you need help, you know, use the videos. Like most things, attempting them on your own is the best way to actually actively learn. So if you want, you can pause the video, try this. Doing the same thing, you basically want to find where only a certain reactant changes, and then use our little formula, right? So if we just kind of start with K, and then you have the reactants with different exponents for the orders. We start with A, let's say. We want only A to change. That should be the first two because B is the same, C is the same. And we have A that's doubling and the rate also doubling. So we have a 2 equals 2 to the x, and then we get x equals 1, first order for A. And then I'll choose maybe a different color for B. So here's A. B, we want A and C to stay the same, which is experiments 2 and 4. We also want B to change, that's important. So B is also changing, and it's increasing by 4. And then here, if we divide the rate 4 by the rate of experiment 2, it's just 1, it's the same number. So when we set this up, the rate change is just 1, or the factor of the rate change. And then we have 4 to the y. So here we get 0. By the way, if you have to solve this with the calculator, if the numbers that you're particularly working with aren't like integers or easy to do, then you have to use log rules. So it's basically like x would be, you can use log or ln of A over ln of B, and that's good to know. Also, anything to the 0 power is 1, so I would probably also know that, and then that one becomes pretty easy. So C, we want only C to change, which looks like 1 and 3. So A is the same, B is the same, C is changing by a factor of 3, and if we divide rate 3 by rate 1, we get a factor of 9. So we have 9 for the rate, 3 for concentration of C. That's a second order relationship here. 3 squared is 9. One thing I should point out as well is that it doesn't really matter which one you divide. So if you divided rate of experiment 1 by 3, you'd basically be 1/9. And then you could have also the concentration by 1/3. It's mathematically the same. And again, even if you had numbers, you're like 0.11 equals 0.33 to the z. Again, you could solve it with this kind of log equation. So here's our rate law, which we can write like this: R equals K A to the first power B to the 0 power C squared, or just oftentimes leaving out the B concentration because it doesn't affect the rate. So that's what a 0 order reactant means, is that if you change the concentration of B, the rate isn't affected. So we leave it out of the rate law. B, what is the initial concentration of C in experiment 5? Going back to our table, we're trying to figure out this value here for the concentration. And you could kind of do it with the conceptual, starting off with the concept of how the rate's changing or whatever, or maybe depending on the problem, easier or equally easy way is just to use the rate law once you've found that. So because we know what the rate law is, we'll just solve for K first. So I'm going to solve for K, and I'm going to use experiment 1 again. So this is going to be the rate, and then K times the concentration of A, and then the concentration of C squared. So you should be able to look at those numbers in from the first row of the table, and then solving for K, 625. Again, this is going to be 1/molarity squared second. Okay. And then in experiment 5, here we know that the rate is 0.0195. Show you. So that's the rate here, experiment 5. And then we have also these concentrations, A and B, and we know what K is, so we can plug that in. And oh yeah, we don't need B, we just need A. So A is 0.05. C, I'll just write concentration of C squared, or you can write X squared. And then solve for that. Don't forget to square root. This should be 0.025 moles per liter. Okay, you can always check by plugging that in, seeing if you get the right rate. Okay, so that's another typical kind of problem. One last one would be maybe considered a little bit different, in that maybe slightly challenging at first if you're doing it the normal way, because when we set this up to solve for the rate law, we can find the concentration, or find the order for A, because the concentration of B is the same in these first two experiments, and A is changing. Actually, for me, it's always kind of easier just to do the bigger change. So going from 2 to 1, that's changing by 2, and then the rate's changing by 4. But again, you could also kind of go like this way, where you go 1/2, and then this way is times 1/4, right? So it doesn't matter which way you do it. We have A 4 equals 2 to the x, or 1/4 equals 1/2 to the x. So we get squared, or second order. And then for B, there aren't two experiments where A is constant, so we can't do it this quick way. But we can still find the order because we found the order for A. So what we're going to do for B is we're going to use the ratio method. So I'll just write use kind of ratio of rate laws. This is usually actually how it's taught. I think probably in your lecture videos you were initially taught how to find their orders by setting up like ratios of rate laws. And all that really matters is that B needs to change. So you could choose 1 and 3 or 2 and 3. Doesn't really matter. I'll just choose 2 and 3. So going from here to here, we have a change in B, and then A is changing, but we know the order, so we'll be able to work that out mathematically. So what I'm going to do here is write rate 3 over rate 2, and just kind of then write the rate law. And these subscripts just mean the values in experiment 3 and experiment 2. Again, we know what the order for A is, right? So we have, want to write X. Otherwise, we'd have 2 unknowns. So now we can plug these things in. So the rate 3 is this. Rate 2 is this. Let's leave the units out. K's are going to cancel. And then we have 36y. Experiment 2, we have 0.36 for A and 0.18 for Y. Okay, so that should be right. You can go and check in the table. Again, K's will cancel, don't need to know what those are. And then again, because we know the order for A, that's gonna be able to be worked out mathematically. And we get something like, for the rate change between those two experiments is 0.88. And then the ratio of the A concentrations is 0.44. This ends up being the same as, we can write this 0.36 over 0.18 as 2, right? And then 2 to the y. So we end up then getting something again that comes down to how the rate's changing and how the concentration's changing. So we end up with y equals 1. So our rate law, we don't need to find K, just writing the rate law, should be second order for A and first order for B. Hope that makes sense. Let me know via email or in the class forum if you have any questions, and I can make videos for other problems if there's particularly challenging one you come across from the textbook or something. Just let me know, and we can try to do a quick video and post it. I'm sure it'll help other people out as well if you have the same question. So yeah, good luck with the studying.